All right, for each of the next couple of videos, we're going to take another carboxylic acid derivative and explore it in a little bit more detail. And so this video is going to be dedicated to the preparation and reactions of acid chlorides. So generally, acid chlorides are synthesized from the corresponding carboxylic acid by reacting it with thionyl chloride. Thionyl chloride being this SOCl2. So here's the mechanism. I think we have enough mechanisms that we need to learn that I'm not going to make you responsible for this one. So if you're interested, you can read more about it in the book, but I'm going to kind of skip over it. All right, so that's it for the preparation of acid chlorides. If we react it with thionyl chloride, that's SOCl2, we can convert the carboxylic acid into the acid chloride. Now, we said that these acid chlorides are pretty reactive. And so just by reacting it with water, we can convert it back into the carboxylic acid. And the mechanism for this is the one that we spent a lot of time on in the last two videos, and that is an example of nucleophilic acyl substitution. And as is typical with the reactions of acid chlorides, we only need the one proton transfer step. So we can do this under basically neutral conditions. So we don't need to start with a proton transfer, so we can start with the nucleophilic attack. Chloride is a good leaving group, so I don't need to protonate it, so I can immediately go into the loss of a leaving group. And then because I have the intermediate here is charged to get the neutral product, we finish it off with a proton transfer. All right, you may have noticed on the last slide, when we reacted with water, we also had pyridine as a reagent. The reason we have the pyridine is that HCl is a byproduct, and so to neutralize it, we include the pyridine, which is a weak base, to neutralize the strong acid that we would be producing otherwise. Okay, so if we react the acid chloride with water, we get hydrolysis, and we convert the chloride to an OH. If instead react it with alcohol, we get alcoholysis, and so we replace the chloride with an alkoxy group. And again, we use the pyridine to neutralize the HCl that we'd produce. Now, it may be helpful to think of the alcohol as being the substrate and the ester as being the reagent. The results are the same. It just may be helpful in some situations to think about it this way. And this is an example where it's helpful to think about it that way. So we're still thinking about alcoholysis of acid chlorides, so we're going to react them with an alcohol. But what's important from this slide is that sterically hindered alcohols react more slowly. So a primary alcohol is going to be selectively acylated when in the presence of a secondary alcohol. So this alcohol is more sterically hindered. This alcohol is less sterically hindered. So the alcoholysis is going to occur selectively with the primary alcohol. And so we'll get mostly this product as opposed to having the carbonyl group coming off of this oxygen. All right, so if we react acid chloride with water, we get hydrolysis. If we react the acid chloride with an alcohol, we get alcoholysis, and we make an ester. If we instead react our acid chloride with an amine, then we get aminolysis, right? But it's exactly the same mechanisms as the hydrolysis and the alcoholysis. We'll have nucleophilic attack, loss of a leaving group, proton transfer. The only difference is with the water and the alcohol, we also added pyridine. Pyridine acting as a weak base to mop up the HCl that we produced. Well, because the amines are themselves weak bases, I don't need to add pyridine because if I just add extra amine, in this case, we'll add 2 equivalents of the amine, it will itself mop up the HCl that's produced. And we can do this aminolysis with just ammonia or with primary and secondary amines. All right, so we've just looked at 3 examples of converting our acid chloride into the other carboxylic acid derivatives that we've talked about. We can also reduce acid chlorides to form primary alcohols. much like we did with carboxylic acids. If we react it with lithium aluminum hydride, and then we need to give it some proton source to finish up the reaction, we can get our primary alcohol. All right, now I do want you to be familiar with this mechanism because it's really mechanisms that we've already learned. So much like the carboxylic acids, we're going to go through the aldehyde as the intermediate, but the conversion of the acid chloride to the aldehyde is just an example of nucleophilic acyl substitution. In this case, the nucleophile is a hydride, and so it's delivered by the lithium aluminum hydride. This is a very basic compound, so under basic addition, so it's okay to form the negative oxygen. So the nucleophile attacks, pi bond becomes a lone pair on the oxygen. Then chloride is a good leaving group, so we have the loss of a leaving group without any protonation. That gives us our aldehyde intermediate. And then these last two steps, this is just a mechanism that we learned last semester. This is just reduction of an aldehyde or a ketone with lithium aluminum hydride. So this is an example of a nucleophilic addition reaction. So again, the hydride acts as the nucleophile, and then we have a proton transfer to finish it off. Now, in practical terms, reduction of acid chlorides by lithium aluminum hydride is not that useful. Right? These acid chlorides generally don't exist in natural compounds, so we have to make the acid chloride from a carboxylic acid. And if our goal was to get a primary alcohol, we could have just reacted the carboxylic acid with lithium aluminum hydride and skipped the step of converting it into an acid chloride. But the reason we talked about that is because an alternate compound using lithium tri-butoxyaluminum hydride, which is just, lithium aluminum hydride is LiAlH4. So we just replaced 3 of those hydrogens with these alkoxy groups. This compound is selectively reactive with acid hydrides, and it won't react with the aldehydes. So when I use lithium aluminum hydride on a carboxylic acid or an acid chloride, I'm going to go straight to the primary alcohol, and I can't stop at the aldehyde. But if I convert the carboxylic acid into an acid chloride and then react it with the lithium tri-butoxyaluminum hydride, then I can stop at the aldehyde. And I know I said I'd make you know the mechanism for the last one. The mechanism for the reaction with this compound is exactly the same as the mechanism for lithium aluminum hydride. Right? This thing just serves as a source of hydride ions. It's just easier to draw the mechanism where these are hydrogens rather than these are tert-butoxy groups. All right, the final reactions I want to consider are the reaction of acid chlorides with organometallic compounds, and organometallic compounds that we've already seen. So we've seen Grignard reagents a lot. If we react an acid chloride with a Grignard reagent, we actually put 2 of the alkyl groups from the Grignard reagent onto the acid chloride. So we convert the acid chloride into an alcohol, but it's going to be a tertiary alcohol because we're going to put 2 R groups in place of the acid chloride functional group. Now the mechanism is exactly analogous to the mechanism that we saw for the reduction using lithium aluminum hydride, except instead of having hydrogen as the nucleophile and making a primary alcohol, we're going to have the R groups from the Grignard reagent acting as our nucleophiles. So with the reduction, this was a hydrogen coming from the lithium aluminum hydride. Now we just have the alkyl anion from the Grignard reagent. It attacks with a nucleophilic attack. We have the loss of a leaving group. And then we have another attack of a nucleophile, right? Again, just replacing the hydrogen with the alkyl anion, and we finish it off with a proton transfer. So this mechanism is exactly the same as the mechanism for reduction using lithium aluminum hydride. Just instead of using H-, we're using a negatively charged carbon. All right, and our final reaction is another reaction of acid chlorides with an organometallic compound, and it's an organometallic compound that we've again seen already. We've seen the Gilman reagent both last semester and this semester. where we have a copper connected to two alkyl groups, and then we have the lithium counteranion, or countercation in this case. Now the difference in the reaction with the Grignard reagent, we're taking our acid chloride and we're adding two R groups and we're getting the alcohol. In the case of the Gilman reagent, we are adding an alkyl group to our compound, but we don't go all the way to the alcohol. We only add one new R group and we stop at the ketone. All right, so this is kind of a nice summary of the reactions that we learned this section. And I'll post this on D2L. If I forget to do that, remind me and I'll post it on there. But we saw how we could make the acid chloride from a carboxylic acid using SOCl2. We could do hydrolysis to convert the acid chloride back to the carboxylic acid. We saw alcoholysis by reacting the acid chloride with an alcohol. We had the aminolysis. We can react it with ammonia or a primary or a secondary amine to get the various amides. We saw how we could reduce it with lithium aluminum hydride to get the primary alcohol. If we use the lithium tri-tert-butoxy aluminum hydride, we can stop at the aldehyde. And then we saw two examples of reactions with organometallic compounds. If we react it with a Grignard reagent, we add two R groups and we go to the alcohol. If we react it with a Gilman's reagent, then we add just one R group and we stop at the ketone.